morning, everyone. Good afternoon, everyone. Hope everyone are doing great at home and expecting you to be safe right at this pandemic situation. Thing is, be safe, enhance your knowledge in this due process, make use of the video classes which are available right now. Yes? Okay, let's start with the topic, today's topic, binary cyclic codes. What are these binary cyclic codes? Before I start explaining, the codes we know are like they are binary. It consists of zeros and ones. Now the term cyclic is a new different thing here. Cyclic codes, what does this define? Yes, this is a form of LBC codes. Binary cyclic codes are the form of a subclass of LBC codes. To call any code to be a binary cyclic, it has to satisfy two of the properties, that is linearity and cyclic shift. What is this linearity and cyclic shift? I'll explain. Suppose I have a set of code words saying okay, and I have a code vector till, suppose I do have a code vector from C1 to C1, C3, C4, Ci and Cj, and I do, let us take generalize it with Ci and Cj. Yes, Ci and Cj. Add these two. Okay, the resultant vector, the resultant code word, whichever I do get, is one of the code words. Okay, it should be one of the code words present in the code vector. Only then we call that code word to be a cyclic shift. This is one of the, it satisfies the linear property. Now with respect to the second thing, cyclic shift. What is this cyclic shift? Let us consider a code word Cj, that is it. Let us consider that it has a binary alpha digits 0, 1, 0. Yes. If at all, if it makes a right shift or a left shift, assuming it to be a right shift, by 1 bit, okay, 0, 1, 0, 1. This resultant code word, okay, this resultant code word has to be present in this code vector. In this code vector, that is when we call a given code word is a binary cyclic code word or not. It has to satisfy both linear property, when it satisfies these two conditions, only then we call that given code word is a binary, binary cyclic code word. I repeat this discussion. Okay. Suppose given a code word Cj, Ci and Cj, when these two code words are added, Ci plus Cj, I will have a resulting code word. Let me take an example here, binary code 1 plus 0, 1, 1. The resultant code word is 1, 1, 1, 1, 1. Sorry. I'll have the 4 ones here. This resultant code word has to be one of the code words of this code vector. Only then we call this to be only then we call that the code word satisfies linearity. How about the cyclic? When suppose I do have a code word 1010, by making a right shift, I'll have a code word 0101. If the resultant of this code word is in any of this code vector, then we call that the given code vector is a code word is a binary cyclic code word. Let us take an example for a better understanding of this linearity and cyclic shift. Let us have a set of code words. Whether this set of code words satisfies a cyclic code or not, let us verify this. Yes. Addition of C1 with any of the code word will always give me the resultant second additive element. That is, if I add a because it will be added with 0, hence it will have the same value. Okay. Now let us take T2 1 1 0 1 0 0 1. Okay. Add this 1 1 1 and this is 1. The resultant code is one of the code word in a code vector. Yes. This satisfies a linear graph. Let us. This is sub condition which we have calculated here. Let us check with C2 plus C4. This resultant is C4 here. This is C4. C2 plus C4. 1 1 1 1. This is 1, this is 0, and this is 0, and this is 1. I will not have any carrier this thing here. 1 plus 1 will be 0 here. Okay. This is the code word of, this is a code word C3, which code word, code vector. That is, now we can say that the given set of code words are binary cyclic. I cannot say it has only satisfied only one of the conditions, that is linearity. Now we have to check with let us consider the symbol C1. Shift either to a right side or to the left side. Either way you shift it, it always has C, and the given code word. Okay. Now similarly, let us check with word 0 1. If let us shift it towards the right side by 1 bit 0 0 1 1. This is a new code word which I have got, and the resulting code word is not present in this given code vector. Hence, it does not satisfy the cyclic shift property. Hence, the given code word does not satisfy Yes, this is one example. I have to take an example, solve an example. I will give another problem. You have to solve it. Check whether this 0 0 0 0 1 0 1. You have to check whether this given. Okay, you have to solve this. Now, I have to check this. Due to this property, okay, due to this property, we can work with respect to, due to this property of binary cyclic code, we can work with, we can fuse it with polynomial, polynomial degrees. Okay, the property of cyclic codes allows us to treat the elements of each code vector as a coefficient of a polynomial degree n minus 1. We can the binary cyclic codes can polynomial degree. Let us consider equal to it can be written in V naught. Okay. Okay. Till V of n minus 1 to x of n minus 1. This is a polynomial factor which can be fused with binary codes in order to calculate a parity check matrix and generator matrix. Okay, the polynomial further polynomial representation with respect to the degree, because v1 x first degree. Okay, is shifted. You can see it here in the PPT. It has been shifted here. Earlier I did have x of n minus 1 into x to the power n minus 1. The coefficient is shifted here, v of n minus 1 plus v naught of x plus v1 of x square plus dash dash till n minus 2 x of n minus 1. For the second degree, it starts with v of n minus 2 and the coefficient x is 0 here, x to the power 0, v of n minus 1 into x plus v naught of x square till v of n minus 3 x into n minus 1. Generalized equation, v of I to the power x is equal to v of n minus 1 plus v of ni minus I plus 1 into x plus, this is a generalized polynomial equations given. Properties, important properties which have to be considered with respect to the cyclic codes. What are these properties? For n comma k, what is this n? N is nothing but the length of the code word. Okay, n is nothing but length of the code word, and k is the information, the number of information bits. Suppose written 7 represents, this 7 represents the number of the length of the code word, and this 4 represents information bits or data bits. For n minus k cyclic codes, there exists a generator polynomial of a degree g of n minus k given by, in a previous equation we did write it here, we did write it with respect to the v of x. The previous slide here I have written it with respect to g of x is equal to g naught plus, because why? Because in the later slides we will be denoting the polynomial coefficients with respect to g. G of x is equal to g naught plus g1x plus g2x square plus till g of n minus k to x of n minus 2. Given any cyclic code, we can write a polynomial. We can generate a polynomial of degree x of n minus k, and is given by this. The generator polynomial g of x of n minus k cyclic code is a factor of x power n plus 1. Okay, and that is given by x of n plus 1 is equal to g of x. This is generator matrix, and h of x is a parity matrix, where h of x is a parity check, a polynomial. Okay, this equation we will use this equation at the later stages. That equation is very much important. The third property is, if g of x is a polynomial of a degree n minus k and is a factor of x of n plus 1, then it generates n comma k cyclic codes. The code vector polynomial v of x can be found by using see here, the code vector can be calculated, can be found using v of x is equal to d of x into g of x, where d of x is equal to a message vector. D of x is message vector of a polynomial of degree, and it is written by d naught plus d1x d2x square till dk minus 1 x power k minus 1. This method generates non-systematic cyclic codes. This is very important. Okay, non-systematic cyclic codes, because we will be generating the code word with respect to, we have two types of codes here with respect to binary. One will be systematic binary cyclic codes, and the other is non-systematic cyclic codes. In order to generate a code vector with respect to non-systematic cyclic codes, we need this equation, that is v of x is equal to d of x into g of x. And the last equation and the last property is, systematic code can be generated. See, I did explain you in the previous slide. We do have two types of cyclic codes there, systematic and non-systematic. We did discuss about non-systematic in the previous slide, and this is with respect to the systematic code. Systematic code can be generated by using r of x is equal to x power n minus k, where n is the number of length of the code word, where n is the length of the code word, k is the information bits, d of x is the message bit, g of x is a generator polynomial coefficient vector. The coefficients of the coefficients of r of x is placed in the beginning of the code vector. Okay, the coefficients of r of x is placed in the beginning of the code vector, followed by the coefficients of message polynomial d of x to get the code vector. With respect to x, okay, this will be r of x. The first three, if at all, if we consider, okay, 4 will be d of x, and the rest of the bits will be with respect to r of x, coefficients of r of x and the coefficients of d of x. Now, let us solve a problem with respect to a code vector. We have to generate a for a given message symbols. For a 7,4 single error correcting cyclic code, see, you have learned about single error correcting cyclic codes, I guess. For a 7,4 single error correcting codes, that is, now our n will be 7 and k will be 4. If we consider k, then n will be 7 and k will be 4 cyclic codes. The d of x is a signal. Denote 1 plus x cube into 1 plus x square plus x to the power 4. Using a generator polynomial, he has given g of x. Write it down. The given data 1 plus x to the power 3. Okay. Find all 16 code vectors. It is nothing but I have to calculate from. If you have given 16 means it will be a combination of 4 bits. Okay, till 1 1 1 1 0 0 0 1 0 0 1 0. This will be 2, and till we have to calculate the code 16 code vectors of a cyclic code, both in symmetric, non-symmetric, and symmetric. Okay. With respect to the properties, we did that the non-symmetric cyclic code is defined by we know what d of x and I know what the g of x is. We will not be considering this g of x right now. Now I know this equation. This is a very important equation which helps us calculate the code vectors. D of x is nothing but the message signal here. Suppose let us consider d of x to be if I have to write this with respect to the polynomial, I have to substitute here. Okay, I'll be having x. If you substitute, I'll be left with the equation. I'll have a polynomial equation x cube. Okay, and see similarly I have got a polynomial equation x cube here, and I have g of x here. 1 plus x cube, I guess. Yeah. Okay. The resultant polynomial equation which I get is x to the power 3, x to the power 4 plus x to the power 6. Now, once I have the equation, now we have to convert this polynomial equation to the binary form. How do I convert it? Since I do not have x power 0 here, it will be 0. Okay. See, x power 1 is also 0. X power 2 is also 0. X power 3 is 1. X power 4 is 1. X power 5 is 0, and x power 6 is 1. I have a coefficient here, x power 6. This is the code. Okay. For the combination d of 0 0 1. The code vector for the message signal 001 is 001101. That is what I have mentioned it here, 001101. Suppose if at all, if I consider the other message signal 1001. Okay, substitute these values in the given d of x. After substituting, I will have x naught is 1 there, x is 0 there, x square is 0. Okay, I'll write that. Oh, sorry. D of x is equal to d naught plus d1 of x. Now let us write this equation in terms of message signal d of 1001. It is pretty simple here. In order to generate a code vector with respect to non-systematic codes, I have 1001 here. Substitute 1 here, that will be in terms of x naught. This is x to the power 0 here. Since I do have x to the power 0, x to the power 1, x to the power 2, x to the power 3. Yes. Substitute it here. I'll have 1 plus 0 plus 0 plus. That's what the equation I have here. 1 plus x cube, and the g of x is given 1 plus x cube. Multiplied with 1 plus x cube. This is the equation which I do have here. After multiplication, 1 plus x to the power 4 plus x to the power 6. Okay, I'll have this corresponding a polynomial equation. After having this polynomial, we have to convert it to the binary. This is the corresponding code word. Once after converting it, see, in terms of x power 0, it is x power 0. I have 1 here. X power 1, I have 1 here value. X power 2, I don't have any coefficient here. X power 3, I don't have any coefficient. X power 4, I do have 1. X power 5 again 0. X power 6 again 1. Okay, this is how the code word is generated. Similarly, with respect to the message signal 1101. With respect to 1101, the d of the polynomial equation with respect to 1101 will be 1 plus x cube multiplied with 1 plus x cube. This is g of x. After multiplication, both of the terms are same. Hence, we will square those terms. 1 plus x square plus x to the power 6. The corresponding coefficient value code vector will be 1 0. I'll have 1 here. X power 1 is 0. X power 2 is 1 here. X power 3 is 0. X power 4 is 0. X power 5 is 0. And last x power 6 is 1. This is how the code vector is generated for only few messages. Similarly, you have to calculate the code vectors for all of these combinations. After calculating for all of the combinations, you have to get this vector, this message signal. Suppose for 0 0, you have to get this code vector. 0 0 1, have to get the same message signal has been written there. 0 0 1 1 0 1. Similarly, 0 0 1 0, the code vector is 0 1 1 0 1 0. You have to generate the code vector. We have 16 combinations here. Yes. You have to generate a code vector for a non-systematic cyclic codes. Now, how about systematic cyclic codes? We have to generate a code vector for a systematic cyclic codes as well. For that, we do have an equation called r of x is equal to x power n minus k into d of x divided by g of x plus q of x is the quotient there. Right now, we will not touch with the q of x, only we will consider x power n minus k into d of x divided by g of x. Now, what is this x power n minus k? Yes, this is x power n is 7 here, k is 4. Substitute it here, we have to multiply x power n minus k into d of x. Let us start generating a code word for the message signal 1001 combinations. Similarly, for 1001 combination, the polynomial equation I'll have is 1 plus x cube. Okay. Since we have to multiply this d of x with respect to x of n minus k. What is this x of n minus k now? 7 minus 4, which is x power 3. Yes. I'll have x power 3 here. X power 3 multiplied with 1 plus x cube, which is equal to x cube plus x power 6. Now we have got the numerator polynomial factor. I do know the denominator polynomial factor as well, which is 1 plus x cube. I'll repeat it once again for the systematic cyclic codes. In order to calculate the code vector Now what will be, there in numerator side we have a multiplication of x power n minus k factor. How do I, what, since we, okay, 1 plus x plus, we have at the numerator side x3 into d of x. I did, we have, this is, okay, generalized form. Now whenever I need a message, whenever I need to generate a code vector for a certain d of 1, polynomial equation for this is, cube. This is what the problem. Not this thing. This is the equation for d of 101. Now, in order further to generate a code vector, I have to divide it x3. I have to divide x3 plus x6 by 1 plus x plus x cube. See here, the division part has been written here. X cube plus x plus 1 has to divide x to the power 6 plus x power 3. Let us consider x cube here, divide it, and I'll have x4 here, and the left out part will be x square plus x. The remainder term, whichever I have is whatever I have is x square plus x. This is a polynomial equation. Again, I have to convert this polynomial equation to the binary form. Okay. Since x square plus x, r will be 3. Okay. Now, do you want? Now the remainder is r of x is, when I convert it to the polynomial, 0. This is the final. Sorry, 0, 0, 1. I did consider it from 0, 1, 1. Okay. Here we had a defined equation saying r, it will be a prefix of d of x message, that is 0, 1. For this is 1, 0, 0, 1. This is a code vector for a message d of 1, 0, 1. Okay. Let us consider some other example now. Other message signal which has to generate a code vector. Okay. Now let us consider the message signal 1101. With respect to 1101, the polynomial factor will be, equation will be 1 plus x cube. Multiply it with x power n minus k. X power n minus k is nothing but x power 3. Multiply it with the d of x. I'll have the resulting vector equation x cube plus x power 4 plus x power 6. I have to divide it with by g of x. G of x, that is x cube plus x plus 1. After division by x3, I'll have 0 here, and hence r of x is 0. Since Okay, the generated code word is, write the prefix of at the prefix of the message signal 1101. That's what here 0001101. This is what the code vector is. Similarly, you have to generate the code vector for all of the 16 combinations as shown here. These are the code vectors for all the 16 combinations right from 00 to 1141. You have to generate the code vector in a similar fashion. You have to generate the code vectors for all the 16 combinations. This is with respect to the systematic and non-systematic cyclic codes. Now, generator and parity check matrix. What is this generator and parity check matrix? We have come across the generator polynomial, that is g of x is equal to, we have read this, g of x is equal to 1 plus x plus x cube. In order to generate a polynomial generator matrix, what we have to do is, we have to multiply by x. For the first row, we have to multiply with x. For the second row, x square. For the third row, x cube. Okay, these equations. Okay, suppose I have a generator. Let us consider assuming a generator polynomial 1 plus x cube. Okay, this is a polynomial equation. In order to write a generator matrix, I have to multiply. In order to generate the elements of the first row, I have to multiply g of x with respect to x for the first row. With respect to the second row, I have to multiply it with x square. For the third row, I have to multiply with x cube. The resultant answers are x into 1 plus x cube, x square plus x cube into 1 plus x cube. These are the polynomial resultant equations, whatever I have got. Once after getting the polynomial equations, I have to convert them to the binary. How? I don't have a term x power 0. Yes? Let us a polynomial equation here. Let us generate a generator matrix here with respect to the first column. The equation of the polynomial equation is x plus x square plus x power 4. Similarly, for the second row is x square plus x cube plus x power 5, x cube plus x power 4 plus x power 6. Polynomial, a binary form of this polynomial equation. I don't have a coefficient with respect to x power 0 here. This is 0. I don't have a polynomial equation here. Hence, x power term will be 0. X power 1, x power 2, x power 3, x power 4, x power 5, x power 6. This is how we have to write it for 7 bits. Similarly, I don't have x power 0. It will be 0 here. X power 1 is 0, x power 2 is 1, x power 3, x power 4, x power 5 and x power 6 is 0. X power 3 plus x power 4 plus x power 5, 0, x power 1 is 0, x power 2 is 0, x power 3 is 1, x power 4, x power 5, x power 6 is 1. I have a coefficient here. This is what the generator can write now a generator matrix for this. G is equal to this is the generator matrix, but this we haven't completed yet because the G has to be with respect to is in the issue. Okay, for to be identity, the diagonal elements has to be 1 1 here for each of the row with has to be Here I do have 2 ones here, I do have 3 ones here, hence it is not an identity. I have to get this identity. This matrix has to be an identity. In order to convert this to identity, we have to add rows here. Okay, what are the rows which will add to get the identity is add R3. Okay, add R3. This is, they have considered the 4 factors here. I did leave one of the g of x here. Okay, I have left the g of x here. G of x, which is this is the second row. This is the second row wherein I did multiply x. This is second row. This is third row. This is fourth row. And my first row will be my g of x, which has a polynomial, which has a binary value 1 1 0 1 1 1 0 1 followed by 0. Okay, 4 zeros here. See, the first row is right, row 1 is right, I have 1 here, row 2 is right. With respect to row 3 and row 4, I do have I have ones here, 2 ones here, which are not, which do not show that it satisfies the identity property. In order to satisfy an identity property, we have to add rows here. With respect to make R3, with respect to the identity, we have added R3 is equal to R3 plus 1. That is triple 1. 4 is not fall for identity. Now, in order to make it an identity, we have to add R4 with R1 plus R2. That is R1, R2 and R4 has to be added so that I'll get an identity matrix. Okay. This is the identity matrix. See, I have got a 1 1 1 here, and I don't have any 2 ones there with respect to the identity. P is the parity check parity matrix, and I4 is the, this is, I have written I4. Why 4? Generally we'll write it as I of k. K defines the number of message bits. That is why only these 4 are considered to be a message bits. The first 3 are considered to be a parity one. That is why P is to I4. Now, with respect to the generation of parity check matrix H, okay, the very important formula in order to calculate the parity check matrix is, that is P x of n plus 1 is equal to g of x into h of x. Okay, I have to calculate now h of x. How is that I will calculate h of x? Now, with respect to the example, we have considered 7, 4 cyclic code. Yes, 7, 4. Hence, substitute n by 7. I have got substituted x power 7 plus 1 with is equal to g of x into h of x. G of x is the polynomial equation which we do have x cube plus x plus 1. Now, with respect to h of x is, I have to calculate h of x. I do know g of x power 7 plus 1 and g of x. I have to calculate h of x. Okay, this is a parity check matrix. After division by x cube plus x plus 1, I will have the remainder is 0, and this thing is x power 4 plus x power x square plus x plus 1. The parity check polynomial is, this is my h of x. Whatever I have this quotient is h of x is equal to 1 plus x square plus x to the 4. For the parity check polynomial is h of x is equal to 1 plus x square plus x to the power 4. In order to generate the polynomial parity check matrix H, I have to write the reciprocal of h of x. Now, what is this reciprocal of h of x? The reciprocal of h of x is nothing but h. We have to write h in terms of its inverse. Equal to h of x has to be divided by x, that is x inverse. Suppose I have h of x as a 1 plus x plus 1 plus x plus okay. This is my polynomial by the factors. Polynomial matrix we have to multiply by because there are four message signals. Okay, x power 4 into h of n minus 1, h of x power 5, x power 6. We will have 3 columns, 3 rows. X power 4, x power 5, x power 6 has to be multiplied with the reciprocal of h of x. Reciprocal of h of x. X power 5 has to be multiplied with h of reciprocal of h of x to get a second row. X to the power 6 has to be multiplied with h of reciprocal of h of x to get the third row. See, after multiplication x of 4, I'll have 1 here plus x square plus x cube plus x to the power 4. This is the polynomial equation which I'll have. We have to convert this polynomial equation into binary form. Since I do have 1 here, 1, x power 1 is 0 here, 0. Hence I have written 0, x power 2 is 1, x power 3 is 1, x power 4 is 1, x power 5 and x power 6 are 0. Similarly, x power 5 and x power, the second rows and third row polynomials are converted to the binary and are written in form of generator matrix H. But the catch is we represent this H by okay, I of k with parity matrix. I of k is identity matrix. Is it identity with respect to the first three columns? No. The very first row is it does have 2 1s there at the very first position and the third position, 1 0 1. Hence, it does not satisfy identity. In order to make it an identity, again we have to add the corresponding rows. Which are the rows to be added there? They are R1 has to be added with R1 plus R3. Okay. After addition, I'll have C here. This is identity matrix. This is in terms of, sorry, I have written it with respect to parity. This is transpose here. Okay. This is a clear identity matrix followed with the transpose of parity. This is parity. I have written. I have written it separately. 1 0 1 1 1 1 triple 1 0 0 1 1 1. And if I take the reverse, the transpose. If I take off the transpose of the parity, I'll have this equation. You can check with respect to the generator matrix. Okay. With respect to the generator matrix, you'll have the same P as that of here, the transpose of P. Now, the very next thing is Design an encoder for a 7,4 binary cyclic code generated by g of x, which is equal to g of x is given as 1 plus x cube, and verify its operation using the message vector 1001 and 1011. I'll show with respect to the message signal 1001. See here, with respect to the g of x, what would be the coefficients of g of x here? How to draw an encoder circuit for a generator polynomial. I have a generator polynomial equation g of x, which is equal to 1 plus x cube. Yes. Now I have to calculate the coefficients of g of x here. What are these? See here, these g0, g1, g2 are nothing but the coefficients of this corresponding polynomial equation. Since I do not have, that is why the g2 is equal to 0 here. Okay, the coefficient what is this is x power 0, 1, x power 1 is 0, g3 is 1. That is what it has been written here. R1, R2, G2, G3. Now, with respect to this thing, matrix, message signal 1001. Let us write the table here. Table in terms of number of shifts, input, shift register contains R0, R1, R2, remainder bits R. Okay. Now, with respect to the initialization, the previously all of the registers they are R0, R1, R2. Initially, these registers R0, R1, R2 are 0 at the initial first shift. It will have a 0. This is a gate. It has a feedback. When it is enabled, the signal is passed. This is modulo 2 addition. Okay. This is message input D. One more thing. Look at here. This is a switch position. This is a position 1 and this is a position 2. Okay. Whenever it is at the position 1, the signal is passed to the gate and it is shifted. The signals will be shifted. I will explain you now with respect to this thing. The input D is 1, 0, 0, 1. Okay. We'll deal with the switch 2 at the last. When it is at the switch 1. Initially, I will be having R0, R1 and R2, 0, 0, 0. Okay. When the switch is at the position 1, the bit 1 is to this gate. Okay. I'll have this value here. This 1 will be pushed to R0 here. Okay. R0. The earlier it had a value 0. It will be shifted here. Okay. I'll have a value 1. I'll have a common value 0 plus 1. Okay. This 1 will have addition here 0 plus 1. It will be shifted to R1. Now Rn has value 1. Similarly, R0 has value 1, okay, and R2. Earlier, the R1 had the value 0. It will be shifted to R2. That is why we'll write it as 0. Did you? I'll repeat it. Now, whenever I send a message, switch is to the position 1. I'll send a message signal 1 here. When I send a message signal 1 here, it passes through this gate when it is enabled high, and I'll have 1 at this position and this position. Okay. Earlier I had a value in the shift register 0. That value, when the value 1 comes here, this 0 will be shifted here to the modulus addition, and I'll have a 1 here. 1 plus 0, upon addition I'll have 1, and this 1 will be shifted to the shift register 1 here. That is why I'll have a value 1 at present value I'll have 1, and previously R1 had a value 0 which will be shifted to R2. That is how the value 0 has been shifted here. Similarly, when I send a message signal 0, the corresponding values we will have. When I shift the 0 value, directly R0 will have because it had 1, then when 0 comes, it shifts to